Okay, it's January, it's 11 degrees outside, but you still want homegrown tomatoes, and your garden looks like that. What the heck are you gonna do? Say hi.
Hi.
Okay, now, all in the cause of science, we're standing inside of a portable greenhouse that we built back during the summer. We've been using it for storage for some of our equipment, but we're actually trying it out for an experiment to see if we can get a larger scale model working with a different heat source that will keep it above freezing inside. Now, as you can probably tell from my breath and, well, the thermometer here, we are looking at an ambient temperature of about 22 degrees. Now, we've already taken some measurements so we can figure out the exact size of the greenhouse. We're going to go inside where it's warmer and do a little math. Right now, in the meantime, as you can see, we're experimenting with one type of heat source. This is the little tea light heater that's been popularized on the net for the last couple of years. Honestly, these aren't the most efficient things on the planet. A lot of people love them, some people hate them. We're going to explain a little bit later why these probably aren't the best items to use in any situation, indoors or out. Now, as I said, the ambient temperature in here is 22 degrees. Excuse me. And we are currently starting this experiment at 5:35. Now, according to the manufacturer's claims, the tea lights are guaranteed to burn at least 3.5 to 4 hours, so we'll be checking back periodically to see how we're doing. Let's go inside. Okay, there are a large amount of different types of candle-powered heaters that are available online in the form of plans. This is the one that we're going to be looking at. It's a very simple design. First of all, we have the base, just basically to protect whatever we sit it on from the heat of the candles. This is a simple loaf pan, already got some tea lights arranged in it. We're going to set a grate on top of this. That just came out of a very small barbecue grill. A small clay flower pot, simple, easy peasy. That centers down right over the candles. Something small like a coin or a bottle cap to cover this hole. Now, the whole idea behind this is the heat from the flames is going to heat up the air inside this pot and thereby heat up the pot. The heat is going to escape around the edges of this pot, which is going to be caught by the much larger pot, which is centered directly over the top of it. Now that hot air is going to swirl around in here, warm up this pot, but the largest amount of the heat is actually going to come out this hole or around the edges. Is it going to work really well? Well, let's apply some science to it and find out. Alright, now we're going to look at a little bit of the math that's going to be involved with this. Now, the first thing we have to do to figure out what it's going to take to heat the greenhouse is figure out the surface area of the inside of the greenhouse. Okay, so now this is going to get a little bit more complicated than one might think because of the type of greenhouse we've got. Now, this, please don't laugh, I know this is not to scale. Now, we've already measured out the greenhouse and got our dimensions. The width of the shortest wall is 72 inches, the long wall is 96 inches. The total height in the center of the greenhouse is 76 inches, but we're dealing with a curved surface. Now, it just happens to turn out that this curved surface here is exactly half of a cylinder. So, first thing we're going to do is figure out the area of that. Now, what we do for that, our formula is going to be 2 pi r squared plus 2 pi r h for height, which in this case, since it's laying over, is the long dimension here. So that's going to give us we add all of these together. That gives us 28,361.28 inches squared. Okay, that's a big number. We got to do something about that. So we take this and we divide it by 144. Anyone tell me? Anyone? Anyone? Okay, we're dealing with square inches, so we can't just divide by 12. We have to divide by the square. So 12 times 12, 144. That gives us 196.95 square feet. Okay. Good. Now we have to look at a couple of other things. Let's get some of this out of the way here. We'll keep that figure because we're going to need it in a second. Alright. Now, we need to figure out what our temperature difference is going to be. Now, if we were going to keep something like, say, tomatoes in the greenhouse, a good ambient temperature would be about 60 degrees. So we need to take the difference of the ambient temperature we want to achieve in the greenhouse from the average lowest temperature the area gets during the winter. Now, I've already looked that up. It's pretty cold around here. The average temperature for our area, according to meteorological data gathered between the year 2000 and 2013, is about 12 degrees below zero. So we want to maintain 60 degrees, and we have to subtract that from the average low temperature. Unfortunately, since we're subtracting a negative, we actually have to add here. So that ends up being 72 degrees. Getting cold just thinking about this. So 14,180.4 BTUs is what we would need on the average coldest day of the winter to heat that little bitty greenhouse up to 60 degrees, thereby keeping your tomatoes nice, warm, comfy, and happy. Alright, it's been a little bit. Let's go outside and see how things are going on. And we're back. It's exactly 2 hours since we began this experiment. The ambient temperature outside has dropped from the 22 degrees it was earlier to 19 degrees. Now, our little candle furnace, heater, whatever you want to call it, is still burning. Looks like we've got about halfway through the wicks, so I'm guessing the manufacturer's claim at a 4-hour burn time is probably pretty close to being correct. Now, the thing of it is, we can look at the thermometer, and it's a little hard to see in the camera, but it does indeed look like we are at 24 degrees in here. But a 2-degree rise over 2 hours does not seem to be very efficient, because if it still follows along those lines, even if the temperature outside maintains itself, we're going to be looking at still a below freezing temperature. which doesn't sound like a good method for keeping your greenhouse warm, especially since we're dealing with such a small area. We'll look at the mathematics in a second here in a little bit more warm environment and see exactly why this thing isn't working. Okay, and we're back. Now, looking like a pretty unimpressive result going on out there. So, let's take a look at the math and see exactly where our little candle heater is starting to fail. The first thing we've got to do is figure out the energy involved. So we have to figure out how much potential energy we have chemically in the fuel, the paraffin. Okay, so tea lights, kind of smallish. Now, what exactly does that mean? Well, at 114.92 BTUs per hour, we're looking at, to make our 14,180.4 BTUs, we're looking at approximately 123 candles. Now, that sounds fantastic enough, but imagine you have to burn that many every 4.5 hours. Doesn't look like a very efficient setup. Not when you can compare it to the cost of running an electric heater. You figure, okay, you can probably get tea lights pretty cheap, you know, a couple of cents a piece. But when you stop and think about it, now we have a little bit of a high energy rate here where we are. We're running approximately somewhere in the neighborhood of 0.603 dollars per kilowatt hour. Okay, yeah, a little over 60 cents. Sorry guys, math gets to me sometimes. Alright, so, and 14,180.4 BTUs. Alright, kilowatt hours equals your BTUs divided by 3.413. Looked that up too. Now, that comes out to 4,154.82, or round it 4.2 kilowatt hours. Now, at 0.603 dollars per kilowatt hour, plus what we pay the average 4% sales tax on the delivery, we're looking at $2.64 added to our electric bill to run an electric heater to get that thing up to operating temperature. Now, there are other factors involved as well. First things first, your biggest energy expenditure is going to be getting it up to the temperature you want to maintain. After that, if it's a thermostatically controlled heater, it's going to kick on, kick off, maintaining the temperature. Also, something to consider is we have a temporary greenhouse out in the backyard, so it's not exactly the most thermally efficient material. Greenhouses can have thermal pane windows, they can have dual polycarbonate windows, which actually reduces your energy factor by about 30%, give or take. So yeah, there are options other than the little tea light heater that everybody's so hot on, pun unintentional, on the interwebs. Alright, let's take one last look at what's going on outside and see just how miserably this thing is failing. And we're back. It's 2 hours later. We're a full 4 hours into the experiment. The ambient temperature outside has dropped to 17 degrees, which means we've lost a total of 5 degrees outside during the course of this. Now, as you can see, we are still burning, but pretty close to running out of juice. Now, we take a quick look at the thermometer, and we'll notice that it is still 24 degrees in here. So we gained and held 24 degrees over the course of 4 hours. Now, once again, not very efficient, because we are still obviously not above freezing in the greenhouse, which means these little candle heaters, not worth the effort. Okay, it's cold out here. I'm going back inside. Okay, so what have we learned? Well, anecdotal evidence is very enthusiastic when it comes to these candle heaters. You can go online, you see them all over the place. But the fact of the matter is, we put the science to it and it just doesn't work. We had a very small greenhouse. That thing is 6 foot by 8 foot. Not a very large area. Even though we were combating the colder temperatures outdoors, we still should have seen a little bit better rise, according to some of the anecdotal reports we've seen on these. Now, what does that all mean? Okay, well, it's inconceivable that you should have to, every 4 hours, burn 123 candles just to get your greenhouse up to temperature. So we know that's not going to work for us. I've had this burning in here inside my rather cluttered library, excuse the mess, for quite a while now. This room is removed from the rest of the house a little bit, so the ambient temperature through the winter usually stays somewhere in the neighborhood of about 63 to 65 degrees. It hasn't budged the thermometer. I may as well have just walked through here with a lit candle rather than just light this thing and leave it on the floor, because there are also safety issues when it comes to these things. I could accidentally knock this thing over getting up. The cat could come in here and knock it over. And what are we looking at then? Not only do I have the possibility of a flaming cat running through the house and a lot of wax to clean up, but I could potentially be standing out in the yard looking at my house burning down. So, is it really worth it? No. There are a lot of low-cost options on the market right now in the form of electric space heaters that really don't burn that much power. Now, we're going to look at other alternative heating sources in upcoming episodes, because the greenhouse is going to be an ongoing experiment for us. We are going to get that thing up and running, and we're going to run it through next winter. And, well, we're going to explore all kinds of options looking at that. So until the next time, we'll see you afield.